I think one part from the one sample test last week, I asked you to remove this condition, correct? Okay, because I think as far as your syllabus is concerned, as long as you are using the sigma from the sample, directly we are going to use t-test, regardless whether the sample size is more or less than 30. Okay, so I think on this part here, so let me delete that part. I'm not saying that that part is wrong, okay, but just to make your life simple to understand, which test are you going to use, Z or T? So as long as sigma is unknown, we are going to use the T test. Okay. When the sigma is known, meaning sigma of the population is known, we are going to use the Z test. Okay, that's it. That is our rule of thumb. Okay, and also the assumption is that it must follow standard deviation. Okay, and the sample must be taken from independent population. What it means by independent? Between sample 1 and sample 2, they are not from the same population. For example, male and female. Okay, you cannot take the male and female from the same population. Okay, it must be taken from a different set of population. Okay, so let's see first in terms of the formula. Okay, of course, even if you were to answer this type of questions in your exam, in actual pen and paper exam, if you were to come to UAM and do the normal exam style, okay, all of the formulas will be provided to you in your exam booklet. So you do not need actually to memorize this formula, even in the real exam. Okay, but what you need to know is which formula to apply depending on the condition or the situation of the question. So of course, you apply the T test when the sigma is unknown. Okay, you apply the Z test that we just discussed just now, okay, when the sigma is derived from the population. So the formula, that's what we mentioned just now, is what we call the pool T test. What does it mean by pool? Meaning you need to combine the value of the standard error. Okay, pool the sample standard deviation. So meaning that this formula is what we call the pool T test. Okay, so the formula for S squared P stands for pool. Okay, sample size number 1 minus 1 multiplied by the variance of that sample. Okay, S1 squared means the variance value or standard deviation squared. Okay, plus N2 minus 1 multiplied by the variance of sample number 2 divided by the combined value of the two samples minus 2. Okay, and then followed by the T test as well. So again, X bar 1 minus X bar 2. Okay, which one is 1, which one is 2 is the same as what we did before, depending how it appears in your H1. Okay, whichever mean that appear first, that will be your X bar 1. Okay, the one that appears on the second, on the next side, on the second value will be your X bar number 2. Okay, so once you have calculated the S squared pool, okay, so plug in into the denominator here, okay, and okay, so S squared P, okay, multiply by the sum of 1 over N1 plus 1 over N2, okay, the product of this, then you need to take the standard, you need to take the square root of that, okay. So that is, okay, if you look at this part here, N1 plus N2 minus 2. If you recall from the previous chapter, okay, in the one sample hypothesis testing, okay, whenever you want to use the T table, okay, if you recall, whenever you want to use the T table, one of the characteristics of the T table is what we call the degrees of freedom, correct? Okay, if yours, let's say in the one sample test, if your sample is 20, then your DF will be 19, correct? Meaning you take the you use the formula n minus 1. This is only for one sample test. If your sample size given as 20, you need to refer to column that refers to 19. Okay, so that is what you did in the one sample test. But for two sample tests, okay, because you have two samples, so your degrees of freedom now will be N1 plus N2 minus 2. So let's say N1 is 10, N2 is, let's say, 12. So the sum of both will be 22. So 22 minus 2, you will get 20. So in the T table, 20 will be your degrees of freedom. So the formula that you see here, N1 plus N2 minus 2, is also equivalent to your degrees of freedom, DF, that you need to refer to the T table later on when you want to determine what is the critical value. Okay, that will be in your step number 4. Okay, so in chapter number 9 previously, okay, your DF will be based on n minus 1 because you are only using one sample. But for 2 sample, you need to refer to this formula here, n1 plus n2 minus 2. Okay, and finally, okay, let's see one example, okay, from this slide. Okay, so you have this one company, okay, manufacturing 2 different type of lawnmower, okay, pemotong apa, ya, rumput. Okay, so you have the time taken to, okay, 5 employees were time using the these 2 machines. Okay, and then 5 employees using this machine, okay, Wellis, and the other machine, there are 6 employees, okay, using this machine. So the time taken is given here. Is there a difference? Okay, so the keyword here, is there a difference? So difference, as what we did before in the previous chapter, the notation for H1 will be not equal to. Okay? Is there a difference between the time between the 2 methods? Okay, so when it comes to is there a difference, okay, so meaning that you need to take the difference between the 2 mean values of Wellis and also Atkins, okay, in this case. So in this example here, okay, so okay, if you look at the slide, okay, they only use the subscript 1 and 2, okay, but I think one of the weakness, okay, from this part here, how they design the H1 and your H0, is that you do not know what is 1 and 2. So in your case, okay, if you were to answer, let's say something like this, you need to show you need to use the appropriate subscript as what you saw in the previous example on the Z testing, okay, on the standard scan and also the U scan, okay. So instead of using just one and 2, okay, you can use the symbol U and S. Okay, so here, okay, if you look at the calculation, okay, Wellis, okay. So if you look at this information here, Wellis and Atkins. So in terms of whenever you want to test a different, actually it doesn't matter whether Wellis minus Atkins or Atkins minus Wellis. But again, it's how you write down your H1. Because when it comes to difference, okay, compared to longer or bigger than or smaller than, that one must be correctly, you must put the notation or the sequence in your H1 correctly. But if you are testing a difference, so it doesn't matter whether you can put, let's say student number 1 put U1 not equal to number 2. Student number 2, she put, let's say the student put, instead of U1, she put U2 not equals to U1. So if that is the way, it is also correct, okay, because okay, if that is the because if you put U2 not equals to mu1, let's say 1 is Wellis, 2 is Atkins. So if student number 1 put mu1 not equal to number 2, then that will be Wellis minus Atkins. If another student put mu2 not equal to mu1, means that 2 is referring to Atkins, then she is referring to Atkins not equal to Wellis. So in the calculation, it will be Atkins minus Wellis, not Wellis minus Atkins. Okay, because whenever you do a two-tail test, a not equal to sign, you are going to test on the both sides of the tail, left and right. So either way, you are going to come out with the correct conclusion as well. Okay, of course, the answer will be the opposite sign. Let's say if you put Wellis minus Atkins, you may get a positive value. Okay, but if you put Atkins minus Wellis, the same answer, let's say Wellis minus Atkins, you get positive 4. But if you put Atkins minus Wellis, you may get negative 4 as the answer, just for example. So But because the nature of a two-tailed test not equal to, you are looking at the two sides of the tail, left or right side in your distribution. So even though the answer will be the opposite sign, depending on how you write your H1, but the conclusion will still be the same, because if you get +4, meaning you are looking at the right side of the tail. But if you get -4, you are looking at the negative side of the tail. Either way, the conclusion will be the same thing, will be you are arriving at the same conclusion. Okay, so for not equal to sign, okay, for a two-tailed test, doesn't matter. Okay, it can be, so even though one student define Wallis as the first sample, okay, Atkins as the second sample, or another student define Atkins as the first sample, Wallis as the second sample. So either way, both are still correct when it comes to arriving at the conclusion. So I think in this example, the book defined Wallis as sample number 1. Okay, so if you look at the calculations later on in the next few slides. Okay, so what I will do is, instead of using 1, okay, the best will be to put here, let's say, use W, and 2 is Atkins. Okay, the same thing here, it will be W. This will be Atkins. So W stands for Wallis method. A stands for Atkins. So you are testing, is there a difference between the mean of Wallis and not equal to the mean time of the Atkins? So if I decide that Wallis appear first in the notation in my H1, so in the calculations later on, okay, in this formula here, X bar 1 will be referring to Wallis, because in my H1, Wallis appear first in this part here. Secondly, it followed by Atkins. So X bar 1 will be Wallis, X bar 2 will be Atkins. So I hope you are clear on that. But if another student, let's say, put the other way around, mu A not equal to mu W, the other way around. So in the calculation, it will be, okay, X bar 1 will be Atkins minus Wallis. Okay, because you define Atkins first, mu A not equal to mu W. So it will be Atkins minus Wallis. Okay, so you must be consistent on how you write down your answer later on. Okay? If the formula, if the Wallis appear first, then it will be Wallis minus Atkins. If Atkins not equal to Wallis, it will be Atkins minus Wallis. Okay, so that is the process of writing, constructing your H1 and also your H0. Okay, so step number 2, you are given the alpha 10%, okay, not 1%. Okay, here I think they are using a bigger alpha, 10%. Okay, and then the test, we are going to use the pool t-test. Okay, so just add the word pool here. Okay, even though you don't put the word pool, you just mention t-test, it still be correct lah. Okay, because t-test okay, is referring to the t distribution. Okay, here again, because you are doing a two-tailed test, so there will be two critical values. One is the positive value, and the second one will be the negative value. So again, as usual, you need to plug in what is the positive value. Here is 1.833, and here will be negative 1.833. Okay, so how do you get 1.833? If you refer to the T table, okay. So if you recall, okay, how many samples that we have here in this question? Okay, we have 5 samples from Wallis, 6 samples from Atkins. So meaning 5 plus 6, you have 11. Okay, 5 plus 6, 11. So if you remember the formula, N1 plus N2 minus 2. 5 plus 6, 11 minus 2 equals to 9. So you are going to use 9 in your degrees of freedom. So here in the T table, okay, you are going to use 9. So 9 will be the degrees of freedom. Okay, you obtain 9 by N1 plus N2 minus 2. 5 plus 6 minus 2. And then 10%, okay, not 1%. And remember, okay, in your T table also, you have the one-tail test or the two-tail test. So you need to refer to the two-tail test part here, not the one-tail test. Okay, because if you're referring to one-tail test 1%, it will be this column here. So you, instead of using 1.833, you might be using 1.383, which is wrong, nah? Okay, because here is 10%, but under one to test. But because the sign of your equality in your H1 you put not equal to sign because you want to test the difference. Is there any difference? So difference means you are doing a two-tail test. Two-tail test, and then your DF you decide to be 9. You obtain by N1 plus N2 minus 2. So 9 under two-tail test, 10%, it will be 1.833. Okay, so that's how you obtain this value of 1.833 on the left side and also on the right side of the distribution. So remember, whenever you are doing a two-tail test, your critical value, your decision rule, okay, in step number 4 must also followed by two different values, one on the positive, one on the negative, more than a positive value and less than a negative value of the same value. Okay. And finally, the calculation. Okay, so here it will be similar to what you did in the exercise 2 days ago, okay, or yesterday when you submitted the exercise. Okay, because the data is raw, meaning you need to calculate what is the mean value, what is the sample standard deviation value. Okay, so I think in terms of deriving, for example, for Wallis X1, you for the Wallis method, you get the mean to be 4, and the sample standard deviation you get 2.9155. The sample mean for Atkins is 5. Sample standard deviation is 2.0976. So in getting these two separate values, 4 and 2.9 and 5 and 2.09, I think should be no problem at this stage. Okay, because if you know how to do it for the previous exercise, okay, calculating the mean, especially the sample standard deviation. Okay, so the same process here. So the only thing that you need to do is first you need to get what is the mean and the sample standard deviation before you can calculate the pool standard deviation. Just follow the formula in the book, okay, and then I think should be fine lah. So if you look at this solution here, okay, N1 minus 1 multiplied by the variance of sample number 1, okay, until the end. So you can see how it is being applied here, simple and straightforward. So the first one will be N minus 1, 5 minus 1. Okay, for Wallis, there are 5 samples multiplied by the 2.9155 squared, followed by sample number 2. There are 6 samples in Atkins minus 1. Okay, multiplied by the variance, divide by 5 plus 6 minus 2. So this is just to get the pool variance or pool S squared P. Okay, so you get 6.2222. So that will be the pool standard deviation. Okay, and then finally, to determine the value of T, or step number 5, calculate the T value and make a decision. So here is also the same, X bar 1 minus X bar 2. So remember, X bar 1 refers to the Wallis value. Why Wallis? Because that's how you write down your H1. You put H1, Wallis not equal, the mean of Wallis not equals to the mean of Atkins. So in the calculation part, it must be also followed by the mean of sample mean of Wallis minus the sample mean of Atkins. So 4 minus 5 divided by the pool variance, the pool standard deviation. Okay, and you get negative 0.662. Okay, if you look at this number here, okay, negative 0.662, you get this number because you put Wallis minus Atkins. If another student were to put the other way around, means that in the H1, okay, in the H1, the student write the mean mu of, instead of Wallis, she put Atkins. Okay, mu Atkins not equals to the mu of Wallis. So in the calculation, it will be the other way around. Instead of 4 minus 5, it will be 5 minus 4. So, but the bottom part will be the same, okay, because this is just the pool variance. Okay, but instead of getting negative 0.662, if the student write down the other way around, she will get positive 0.662. So is this right or wrong? Both are still correct, because if you get the one like in the slide, okay, which is negative 0.662, you are going to compare on the left side of the tail. Okay, but if you get positive 0.662, you are going to compare on the right side of the tail. Okay, either way, the conclusion will still be the same. Okay, but remember, if you put 5 minus 4, this must be also correctly represented in your H1. Okay, you cannot put in your H1 values not equal to Atkins, but in step number 5, you put the other calculation, meaning you put values Atkins minus values. So this is wrong. Okay, so if you write your H1 Atkins not equal to values, so it would be Atkins minus values as well. Okay, so the sequence must be consistent. Okay, so what you write in H1 must be consistent with the calculation in step number 5. So if you follow the one in the slide here, you get negative 0.662. So again, it will be a 3-part answer. First, whether the value, the calculated T here is inside or outside the area of rejection. Secondly, whether you reject or do not reject. And thirdly, the meaning of the conclusion. So you can see here clearly. So 0.662 negative is outside the area of rejection. So we do not reject. Okay, do not reject H0. So in the third part, because we do not reject. Okay, so again, go back to your H1. Okay? Whenever you have finished your calculation and you want to write your H1, you want to write the conclusion in the third part of step number 5, always go back to your H1. So in our case here, we do not reject. So do not reject means we cannot support H1. So your conclusion for step number 3, okay, in step number 5, part number 3 just now, because we cannot reject, we conclude that the mean of values is not equal to, there is no difference. Okay, there is no difference between the mean of values and the mean of Atkins. Okay, so be careful because the word difference is already a negative thing. There is not. Okay, you cannot use there is not equal. Okay, so there is no difference. Okay, so there is no difference between the mean of values and the mean of Atkins. If you reject means there is a difference lah. Okay, because H1 means the mean of W tak sama dengan the mean of Atkins. Okay, not equal to the mean of Atkins. But because we cannot reject, means we cannot say that there is a difference. If you reject means there is a difference. Okay, so in part number 3, if in your conclusion, okay, because we cannot reject H0, so we conclude that there is no difference. Okay, there is no difference between the mean of W or values and the mean time of Atkins. Okay, so that is using the pool t-test. Okay, so I think both. So first, what we have covered today, first we discussed on the Z test. Okay, when sigma is given. Okay, so under sigma is given, we are just using this simple formula. Okay, again, whether you are using Z or T test, okay, the main thing is how you construct your H1. Okay, so in the first example under Z, the keyword here is longer. Okay, so we use the sign bigger than. Okay, the right side, I mean longer or bigger than. Okay, but the second thing that you need to be particular is that the order of how it appears in your H1. Okay, because in this example, I think it's very clear. You want to test that standard time is longer than the U time. Okay, so it will be standard appear first. So because standard mu s appear first, followed by mu u. So in your calculation, it will be x bar s minus x bar u. So for a one tail test, whether longer or smaller than, I think it is quite clear. You need to follow what the question wants you to test. But for a two tail test, using the from the keyword, is there a difference? So this is something that you need, that there could be a difference in the approach between different students. So between, this is proportion. We haven't discussed proportion yet. Okay, so in this particular example, is there a difference? Okay, so the way you write your H1, the order which mean appear first, whether mean W or mean A appear first, that will also affect how you write down your answer in step number 5. Okay, so in this particular example, we choose to the slide put mu Wallis not equal to mu Atkins. So it will be mean of Wallis minus the mean of Atkins. Okay, and then you need to be consistent until you arrive at the conclusion. Okay, so I think that's it for today. So we will continue on next Thursday with the dependent and independent t-test. Okay, and hopefully maybe we can continue finishing up in the syllabus. Okay, depends on, I think if we finish earlier, then you have more time to do your assignments. Okay, so there's no point delaying or teaching slowly when we can finish some of the syllabus earlier, so that you can have more time maybe to do other assignments for other subjects as well. Okay, so we stop at this slide.